Hello, good evening, everyone. My name is Sonal. I and my team members are here to present project on analysis of factors im- impacting mortality risk. I would like to thank Sharat sir for sponsoring our project and 360DigiTMG for giving us this wonderful opportunity. Also, I would like to thank Stuart's mentors, Mr. Raju and Ms. Gomti, for their great support. I would like to introduce me and my team members. Myself, Sonal, Shanmukpriya, Venkata, Raghu, and Shahan. These are the contents of presentation. Project overview and scope. What is the project goal? CRISP ML methodology, technical stacks that we have used, project architecture, data pipeline, data preparation, feature importance, individual disease impact, impact on age group and gender, feature selection, final interference, and conclusion. Our project aims to address the impact of disease on mortality risk to help Health Service of UK client to better understand the disease which influence the mortality risk of a human. Scope of this project is accessing the top 10 diseases that impacts the mortality risk based on the age group and gender. Mortality refers to the number of deaths that have occurred due to the specific illness or condition. Mortality rate is getting impacted by different combination of disease spread among different ages and groups. Our main objective in the project is here we are following a CRISP ML methodology for the project. Since the scope of the project is only factor analysis, we have restricted our work to the business understanding, data understanding, and model building part. Mentioning about technical stacks, we have done programming in Python using Google Colab environment. Within Python, we have used packages like pandas, NumPy, Matplotlib, Seaborn, sklearn, feature selection. We have done visualization using Python, Microsoft Power BI, Tableau, Matplotlib packages, and Seaborn packages. Moving towards the data pipeline, our dataset consists of two types of data types, integer or float type. The dataset consists of 10,000 rows and 84 columns. The data is about various patients and their medical histories versus mortality risk. Moreover, various medical tests such as asthma, B12, beta, BMI, BP, etc., and also habit records such as smoker, alcohol, etc. Thank you. Now I would like to request Shanmukpriya to continue.
Thank you, Sonal. Hi, good evening, everyone. So this is the project architecture. Firstly, we will be understanding the main business objective and the columns present in the dataset and their data types. Next, we'll be dropping the irrelevant columns which are not required for drawing further inferences. Next, we'll be model building, and lastly, we'll be checking the efficiency of the model. Okay, so this is the description of the data. We have divided the data under test, disease or disorder, patient, demographics, hospital visits, habits, surgery, drugs or vaccination, and others. Now I'll be explaining the data preparation part. The data which was used to train the model consisted of 1,000 rows and 84 columns. Firstly, we performed data cleaning, where the columns containing null values were removed. From the given data set, there were 8 columns which was having 9,999 null values, and these null values were removed. There were no outliers in the given data set because most of the data which was provided was categorical. The columns containing numerical data does not have outliers. Hence, outlier treatment was not required. Data splitting was not necessary here because we are trying to understand what factors primarily influence mortality risk rather than predicting a variable. Next, we'll see about identifying the numerical, text, and categorical columns. Numerical columns such as inpatient history, outpatient are irrelevant details because they deal with the patient visit history. String columns like patient ID are again irrelevant details. Categorical columns like diseases and other medical tests are represented in binary categories indicating the presence or absence of the disease or test. The target column is the mortality risk column, which is in the numerical form. Now let's see the important observation on the mortality risk column. So here only the first 120 rows of the mortality risk column have entries greater than 0.1. Hence, more weightages should be given to the diseases that are contributing to the mortality risk in the first 120 rows. It was found that the first 120 patients have many diseases present at once. Hence, it would be better to find commonalities across all the approaches and give a conclusion on the feature importance. Thank you. Now, Venkata will be taking forward.
Thank you, Shanmukapriya. Hello, everyone. I am Venkata. So far, we have gained business and data understanding. Now, we move further to perform feature engineering to assess the diseases that impact mortality risk the most. To achieve the same, we have adopted different approaches to come to a common conclusion. At first, we assess the average mortality risk for each individual disease for a given age group and gender. Later, we have adopted approaches like random forest regressor, select KBest features method, Pearson correlation to understand the potential impact of individual disease on mortality risk. The results of all the approaches are tabulated to conclude on the diseases that impact mortality risk the most. This is the overall outline of what we have done. Now, I am going to talk about assessment of impact of individual disease on mortality risk. To understand the impact of features on mortality risk, we consider the average mortality risk as the parameter and plot it for different age groups. We divided the age groups into young, adult, and old. The presence of disease is indicated by 1 and its absence is indicated by 0. The color coding is indicated in the visualization. The left bar indicates the scenario where the disease is absent, and the right bar indicates a scenario where the disease is present. The increase could be due to the given disease or due to the combination of diseases. To decide the impact of individual disease, we see the difference of average mortality risk in the two scenarios. The diseases with a significant difference have the potential to be the strong impactors. Rest of them definitely do not have that impact. This way, we eliminate the mediocre and least impactors. It has been observed that old age group are having significant values of average mortality risk compared to other age groups. Hence, we assess the old age group to decide the impact of that disease. If the difference of average mortality risk in both the scenarios is greater than 0.05, that particular disease can be a strong impact. In case the difference of average mortality risk is between 0.03 and 0.05, then that feature has mediocre impact. Anything lower than 0.03, the feature has weak impact. The difference has been estimated based on the blue and the light blue bars. The visualization in the next slide are of the features that have strong impact on mortality. ACE, the column ACE seems to have a strong impact due to the significant difference in average mortality risk observed in the visualization. From this visualization, we can infer that AF column has significant impact as the difference of average mortality risk with the presence or absence of the column is found to be greater than 0.0. Likewise, assessment has been made for all the columns in the data, and the top few columns impacting the most are shown in the presentation. As shown in the slides, these are the top features impacting mortality risk. The final observations are dementia, bone sparing columns had significant impact exclusively on old age groups. Feature columns ACE, AF, CHD, HF have impact on both old and adult age groups. The impact of anticoagulative, stroke, cancer columns is there on all the age groups. Now, Prabhu will be taking over the analysis of mortality risk with respect to age, gender, and disease.
Thanks, Venkat. For this analysis, we have used Tableau tool to visualize the data. Again, age group is divided into three groups as young, adult, and old. If you see the visualization, rows represent all people who are suffering from particular diseases, and bar represents the average mortality risk. To have better understanding, we have numerical representation or crosstalk of this visualization. Summary of those visualization are shown as gender 2 represents the male and gender 3 is female. Patients with male gender of young age group, that is 0 to 20, having diseases, cancer, palliative, along with smoking, average mortality risk of 12.51%. Patients with female gender of young age group having diseases, cancer, palliative, along with smoking, have average mortality risk of 4.81%. Patients with female gender of adult age group, that is 21 to 50, having diseases, asthma, cancer, cholesterol, palliative, renal, thyroid, along with smoking and alcohol consumption, have average mortality risk of 25.002%. Patients with male gender of adult age group having diseases, cancer, cholesterol, palliative, renal, along with the smoking, have average mortality risk of 7.23%. Patients with male gender of old age group, that is greater than 51, having diseases, cancer, cholesterol, palliative, diabetes, hypertension, renal, stroke, thyroid, along with smoking, have average mortality risk of 37.92%. Patients with female gender of old age group having asthma, bone sparing, breathlessness, cancer, cholesterol, cervix removal, dementia, fracture, palliative, hypertension, renal, heart, thyroid, along with smoking and alcohol consumption, have average mortality risk of 63.59%. This group have highest average mortality risk. From these above diseases that we encountered from the age group and gender analysis, we are going to make individual analysis. If you see the visualization, color represents gender. That is, blue is male and orange is female, and red is the other gender. And size of the bubble represents the age group and young adult and old, which can be seen from the right side of the visualization. If you see the visualization, male and old age group suffering from dementia have average mortality risk of 16.75%, and female of same age group have 16.38%. And in next visualization, male and old age group admitted or in palliative care have average mortality risk of 17.33%, and female of same group have highest average mortality risk of 19.83%. Like this, we have analyzed for all the diseases that we got from the analysis based on the age and gender group. Female with palliative of old age group have highest average mortality risk of 19.83%. Next, for feature selection approaches. So far, for feature selection, we have used two models to get the feature importance score. First is a random forest regressor, from which we have plotted feature importance plot. This has been illustrated in the slide. According to the feature importance plot, top 10 factors that are influencing mortality risk are dementia, palliative, age, cancer, bone sparing, stroke, breathlessness, chronic kidney disorder, heart, etc., and others. And next, for second approaches for feature selection is KBest features, which gives the scores for the factors or features influencing the mortality risk. Snapshot of scores can be seen in the slide. Both the approaches are almost giving the same scores for the features. For choosing the factors or features, first built model should be acceptable, which can be commented by calculating the root mean square value. Trained test data was split into 70 to 30 ratio. For random forest regressor, RMSE value is 0.009865, and for KBest it's 0.0081. So both have very less magnitude, so they can be acceptable. Now, rest approaches will be taken over by Venkat.
Thank you, Raghu. So far, we have taken different approaches to estimate the diseases that are top impactors. We have also used Pearson correlation-based approach to assess the impact of individual column on mortality risk. The mortality risk column is set as the target column and correlation coefficient is computed for each feature column. The top 20 features are considered to have strong impact on mortality risk and the next 20 are considered to have mediocre impact. The last features, that is the rest of the 20, are considered to have weak impact on mortality risk. We also made a correlation heat map that assesses the relationship of different features with each other and with the target column, which is mortality risk. We have come up with a method that could achieve the task of feature elimination. This could be achieved using value counts function. It gives an insight on how many values per category are present in each column. Since our data is binary, we get to know the number of ones and zeros in each column. All columns where more than 9,990 zeros are observed are to be assessed carefully, as these columns are constant variance columns and we can't make decision with these columns due to limited information. One such column that we observed is the bone sparing column, which has 9,991 zeros and 9 ones, and it turns out to be the strongest impactor of mortality risk in other approaches. After analysis using different approaches so far, we tabulated the observations from all the methods we used and observed the top 10 impactors common among the different approaches we used. The following are the final conclusions that we derived. The top 10 diseases were observed to be dementia, palliative, stroke, CKD, HF, breathlessness, cancer, and bone sparing. The top impactors on mortality risk were dementia and palliative. They had the highest impact with mortality risk percentage to be 16.75 and 19.83 respectively. Old age group people had the highest average mortality risk. Among males and females, we observed that out of the above 9 diseases, 6 diseases were predominant in women, so they are more prone to life risk. If you have any questions, feel free to ask. Thank you all. Thanks for 360DG management and mentors for giving such an experience of working on healthcare and life science project. Any queries related to the presentation, you can feel free to ask now.